Hello, math humans. We're going to do 5.1 today. We're going to be talking about natural logs and then differentiation of natural logs. Our objectives are that we're going to review properties of logs, and then we're going to differentiate our log functions. So if I have the integral of x to the n dx, this is just a remember, x to the n plus 1 over n plus 1 plus c. So remember that integrals go up, and then I would tell you that if I have x to the n and I want to take the derivative, then it's going to be n times x to the n minus 1. So derivatives go down in power, integrals go up in power. If we think about our function, y is equal to the natural log of x, that particular function is going to cross at x is equal to 1, and it's going to look like this. Remember that logs are undefined for x is less than 0, so you can't take the log of a negative number. And then in pre-calc and in algebra 2, we did a lot of bouncing between forms, between exponent form and log form. An exponent form would be e to the y is equal to x. So let's talk about some properties of our natural log function. UR, spelling is optional, function. Okay, so if we look at the properties of the natural log function, the domain of this function is from 0 to infinity. The range is going to be all real numbers, so negative infinity to a positive infinity. We know that f is going to be continuous. It is increasing over its domain. And then we know that it's 1 to 1. And if you'll remember, 1 to 1 means that the function has an inverse. Okay, and both the inverse and the function are actually functions. F is concave down over its domain. Okay, so those are things that we know about the function. We know that if f of x is equal to the natural log of x, f prime of x is going to equal 1 over x, and then f double prime of x is going to be a negative 1 over x squared. Okay, so those are some things that we know about the function y is equal to the natural log of x. So now let's look at some properties, and I'll change colors of pens in a minute, my bad. Properties of logs. Okay, I know that the natural log of 1 is 0, and that's actually really helpful to remember, especially if we're on a non-calculator portion of our test. If I have the natural log of a times b, that's the natural log of a plus the natural log of b. And sometimes with our derivatives, our equations can get wicked complicated, but if I use my properties, it makes my life so much better. The natural log of a divided by b is going to be the natural log of a minus the natural log of b, and the natural log of a to the n is going to equal n times the natural log of a. So those are just some properties of logarithms that we've learned in previous math courses that we need to go back and remember. So for our first example, I'm just going to do a couple of problems just using those properties of logarithms. So in this one, I want to expand some logs. And so for A, I'm going to have the natural log of the square root of 3x plus 2. Well, when I expand that or rewrite it, I can write this as 3x plus 2 to the 1/2. And then this is going to be 1/2 natural log 3x plus 2. Okay. The next one, what if I had the natural log of x squared plus 3 divided by 2x minus 7? Then this would be, using our properties of logarithms, the natural log of x squared plus 3 minus the natural log of 2x minus 7. And my last one in this section, what if I have the natural log of x squared plus 3 squared over x times the cube root of x squared plus 1. Okay, so if I managed all of these numbers, this 2 gets to go out front, so it's 2 natural log x squared plus 3 minus the natural log of x minus 1/3 natural log x squared plus 1. So being able to use the properties of logarithms is going to help us significantly when we start trying to take derivatives and then eventually integrals of logs. The derivative of a natural log is actually pretty easy. So I have the derivative of the natural log of x is going to be 1 over x. And of course, x has to be greater than 0. And then if I add a u, because I can, then the derivative with respect to x of the natural log of u is going to be 1 over u, and then the chain rule times the derivative of u. And again, u has to be greater than 0 because negative logs don't exist. Alrighty, I have a bunch of quick little examples. So example number 2, I'm going to take the derivative of the natural log of 2x. So the derivative is going to be 1 over 2x times the derivative of the inside, which is 2. 2's cancel, so this is just 1 over x. Okay, so I switch pens. Example number 3, and I'll move my paper in just a sec. Example number 3, I want to take the derivative of the natural log of x squared plus 1. So the derivative is going to be 1 over what starts inside, and then times the derivative of the inside 2x. And so I would just write this as 2x over x squared plus 1. Okay. My next example, example number 4, hopefully you can see that green. I think you can. I want to take the derivative of x natural log x. So this is the product rule because I have this term times this term. So it's going to be the first term times the derivative of the second plus the second term times the derivative of the first. Clean it up a little bit, and this is going to be 1 plus the natural log of x. Okay, so that was pretty easy. All right, let me go to a different page as we start our next example. So example number 5 is going to be the natural log of x times x squared plus 1 squared over the square root of 2x cubed minus 1. And I want to find the derivative. Oh man! So this is one of those situations when you see something like this, you would have a chain rule, a product rule, a quotient rule. Your life would be miserable. But if you use the properties of logarithms, hallelujah, the problem gets easier. So I'm going to start by rewriting. And so I'm going to say that f of x is equal to the natural log of x plus 2 natural log x squared plus 1 minus 1/2 natural log 2x cubed minus 1. And now if I want to find f prime of x, it's going to be 1 over x plus 2 over x squared plus 1 times 2x minus 1/2 times 2x cubed minus 1 times the derivative of the inside, and I'm going to get 6x squared. I think, did I do my math right? I think so. Okay, and now I just clean it up, and so this is 1 over x, and this is plus 4x over x squared plus 1. 2 goes into 6 3 times, so minus 3x squared over 2x cubed minus 1. Significantly easier than trying to do the product and the quotient and the chain. Your life would have been miserable. So remember that when you have complicated looking expressions, it might be really nice to attempt to take rewrite it using the properties of logarithms. Example number 6, we're going to get y is equal to x minus 2 squared over x squared plus 1, and I want to find y prime. Okay, and again, this looks like a really complicated problem, but if I use the properties of logarithms, it's actually pretty easy. So because this is set up a little bit differently, I'm going to take the natural log of both sides. So I'm going to say the natural log of y is equal to 2 natural log x minus 2 minus 1/2 natural log x squared plus 1. Well, now if I take the derivative, I'm going to get 1 over y. Remember, when I take the derivative of a y thing, then I generate a dy dx. Remember, that's implicit differentiation. And so this is going to be 2 over x minus 2 times the derivative of the inside minus 1/2 times x squared plus 1 times the derivative of the inside, 2x. And I'm just going to write that this is 2 over x minus 2 minus 2x over 2, and then I have my x squared plus 1. Okay, so I guess those 2's would have canceled. Okay, all right. But the goal was to find the derivative, so we're not quite there. So I'm going to write dy dx is equal to, and I'll explain where the y went in just a moment, x minus 2, I'm going to put parentheses, minus x over x squared plus 1, close parentheses, and I'm going to multiply by y. So I cross-multiplied and took the y to the other side of the equation. But you can't leave it like this because we know what y is. Y is this expression right here. So I'm going to write that dy over dx is equal to 2 over x minus 2 minus x over x squared plus 1 times y, which was x minus 2 quantity squared over the square root of x squared plus 1, and this is going to be my final answer. Okay, I could try and simplify, but for the majority of the time I would tell you all done. Because now if I wanted to evaluate the derivative at a given point, it's relatively simple to do that. Okay, so anytime you have a really complicated situation, one possibility is simplifying, as we did in example number 5, by rewriting with our properties of logarithms. And the other one is simplifying with the properties of logarithms and then taking the log of both sides. Okay? All right. I have 2 more examples for us, and then we are done. So example number 8 says f of x is equal to the natural log absolute value cosine of x. Okay? So when I do this, this gets to be a little bit entertaining, and I want to find the derivative. So the derivative is going to be 1 over the cosine of x times the derivative of the inside. And actually, I think that's not absolute value. I think those are just regular parentheses, times the derivative of the inside, which is a negative sine x. Well, sine divided by cosine is a negative tangent of x. So I would write that f prime of x is a negative tangent of x. All right, one more example. Example number 9 says find the relative extrema. And that means that we're going to do the first derivative. My equation is going to be y is equal to the natural log of x squared plus 2x plus 3. So if you'll remember, if I want to find extrema, I have to find the derivative. And so my derivative is going to be 1 over x squared plus 2x plus 3 times the derivative of the inside, 2x plus 2. So I'm going to rewrite this as 2x plus 2 over x squared plus 2x plus 3. Okay? When I set this equal to 0 and cross multiply, my critical value is going to come from the numerator. So I'm going to get 2x plus 2 is equal to 0, 2x is a negative 2, x is a negative 1. And so then if I evaluate my function, so maybe I do a negative 10 and a positive 10, and I do f prime of a negative 10, And when I do that, I'm going to get that it's decreasing. And if I do f prime of a positive 10, I'm going to get that it's increasing. So therefore, I have a relative minimum at x is equal to a negative 1, or I could say I have a relative, let me scoot it up, minimum at negative 1 f of a negative 1. Okay, so you could report your answer either way. Alrighty, that's it for today. I will see you soon.